Welcome to example number 2. This question is about the first law of thermodynamics, and often students have problems understanding what to use as the appropriate signs when we talk about heat and work done. So let's take a look at example 2a. We have a system that absorbs 500 calories of heat at the same time does 400 joules of work. So imagine the system as a gas in a piston. And there's a picture shown here to the left of a piston, and this is the shaft that can move up and down, and it is absorbing 500 calories of heat. So heat is flowing into this system, and so hence Q is positive 500 calories. And at the same time, the system, the gas, does 400 joules of work. Is that positive or negative? Well, you have to understand what is doing the work. And in this case, it's the gas that is expanding and doing work on the surroundings. So this shaft is moving upwards, and so this is going to be a negative work done because the work is done by the gas. So now applying the first law of thermodynamics, the change in internal energy of the system is equal to the heat flow in or out plus the work done by the gas. Now, you may notice that we need to have the units in both have to be the same. So this is in 400 joules, but this needs to be changed to calories, to joules. So 1 calorie, hopefully you recall, is 4.184 joules. So we'll need to convert those calories to joules. So in our next line here, our change in internal energy will be equal to 500 calories, but then multiplied by 4.184 joules for every calorie, plus a work done of 400 joules. But it's negative because the system is doing work on the surroundings. And then we have the 500 calories multiplied by 4.184 joules per calorie gives you 2,092 joules, and then negative 400 joules, which gives you a change of internal energy of 1,692 joules, which we can round off to approximately 1,700 joules. Okay, in 2b now we have a system that is absorbing a heat of 300 calories, so that, again, that is positive. But at this time we have 420 joules of work done on it. That means that this piston shaft is moving downwards. Over here in the other case, the piston shaft was moving outwards, so this was expansion in the first example. Now we have a compression because there is some external force that is doing work and compressing the gas. So in this case, the work will be positive 420 joules. Now the first law of thermodynamics is Q plus W. In this case, Q is 300 calories multiplied by 4.184 joules per calorie. And then now we're going to be adding 420 joules to this. And so we get 1,255.2 joules when you convert the calories to joules plus 420 joules. And you add those two together, you'll get about 16,000 or 1,675.2 joules, which is roughly 1,700 joules. In the next case, we have 1,200 calories that is removed. So heat is flowing out, so this is a negative 1,200 calories. And the volume is held fixed, which really tells you that the work will be 0. Remember that work is equal to, in a general way, I suppose we could say, is just really the negative area under the PV curve. But you can also say as the negative pressure times the change in volume. But the change in volume is 0, so there is no work done. So any process where the volume remains constant, there'll be no work being done. Remember, there's no displacement, so hence no work done. So now the internal energy change of the system is going to be Q plus W, but W is 0. So really, it's just the heat that was removed. That's negative 1,200 calories, which, let's convert that to joules. So we're going to be multiplying by 4.184 joules per calorie, which gets you an answer of negative 5,020.8 joules, or roughly negative 5,000 joules. And that's it for this example.